Do you have the coffee?
I had the coffee.
Okay. So, good afternoon, everyone. Welcome to the Economics Research Institute at UNAM. We are glad at this time to initiate the first seminar of applied econometrics at the Institute. And we are just starting with a distinguished professor of the University of California at Davis. He is a specialist. I think that I know that most of you are studying applied econometrics in your undergrad courses or your grad courses. So this is a very rich presentation that we are going to have from Professor Colin Cameron. I'm going to talk a little bit of his biography, and then I will give the word to Carlos Alba, who is a representative from the School of Economics. Okay, so Colin Cameron is a distinguished professor of economics in the Department of Economics. He works on theory for cross-section data, especially count data, cluster robust inference, and applications to labor and health economics. This time he will speak about machine learning, that we all know want to learn a lot about this very hot topic nowadays. I will give the word to Carlos Alba so that he can give us some words from the School of Economics that we are working closely with them. Thank you.
Hi, thank you very much. On behalf of Lorena Rodriguez, Director of the School of Economics at UNAM, I want to welcome you all, and I want to tell you that we are very excited to see so many of you here. We're facing a new frontier, a brave new world in the field of econometrics. Econometrics has always relied on mathematics and on computing power to carry out predictions. But the latest developments in the last 20 years, maybe even more in the last 5 to 10 years, have set a new panorama for the discipline. And we are very glad to see so many of you here. And we hope that this experience will be very enriching. We want to give a very special thanks to Dr. Colin Cameron for being here and for sharing with us his knowledge. Thank you very much.
Okay, well, thank you so much for inviting me. And Director Vargas has been very nice in showing me around some of Mexico City's history. And also had a chance to go around the UNAM campus, which is very impressive. Okay, and I'm quite relieved to no longer see a photo of what I looked like 10 years ago. Okay, so machine learning, what I'm mainly going to talk about is this overview. I am not an expert in machine learning, but a big part of my what I've done is writing books to help other people. And the second edition of Microeconomics Using Stata, I wanted to include machine learning. So I learned it, and I've given presentations in a number of places because I think it's very important, right? Tool, not only that we should know it in economics, but if we don't use it, other people will use it to economics problems, and they won't necessarily understand the things that we understand in economics, such as, you know, what one person does in isolation may spill over to others, right? Or that there's a difference between association and causation. Okay, so let me go to my website briefly and say that if you're interested in this topic, down here I've got machine learning. I'm not going to enlarge it. I'll just say there's a machine learning here. If you click on that, then you'll get into some slides I have. And the slides that I'm going through at the moment are these ones at the top. So they're the ones I'm going through. And then supplementary material, I've got a lot of stuff, but I gave a short course in 2022, and that has a lot more here with slides and so on. Okay. So let me go to my talk. Which one do I want? Intro, very brief. Control L. Okay. So I find it easier to move. Let's see if I can still be heard. Okay. So, right, the first thing is that the term used is machine learning because it is the machine learning from the data, right? So normally we say, well, we're economists, right? I know, if it's consumer demand, I should put in there prices of own good, complementary goods, substitute goods, income. And then if I'm really clever, I should choose, oh, great, a functional form that is one where if you double all prices and double all income, there's the same real demand, right? The machine throws all that out. You just give it all the data. You give it the price data, you give it the income data, and it figures out, what's the best predictive model for individual demand, okay? And also, a lot of the, as I've got here, a lot of this is coming out of computer science, right? And so they have different terminology. And the big thing of this talk is just to demystify it, right? What are these terms like supervised learning, unsupervised learning, and so on? And if you know linear regression, which is what we teach with an economics degree, this is easy, right? But a lot of other people coming into this may not have even had any statistics, right? If you're a computer scientist, you don't necessarily have seen regression and so on. But we've got a really big head start. Okay, so right, so this is what I've said. We would have some idea about the structure and we would put it in. Machine learning methods instead start with a very flexible model. And then what they're doing is they're doing a lot of data mining. So they're chasing, if there's an outlier, they're going to take account of it. So and you don't want that. So they have methods to try and get away from, being too greedy at chasing each data point. And a big change is that whereas we use, typically statistical significance is the, p-value more or less than 0.05 to refine our model, they look at prediction. What's the predictive power of the model, right? So that's a big change. Okay, so, right, so that's what I've said. So the notation I'm going to use, I think this does a light, yes. We're trying to explain a single variable y with a group of variables x, okay? And we're going to try and have as flexible a functional form as possible, right? Whereas typically we'd have, let's say a linear regression here, where the x's could be nonlinear transforms of original variables, but we'd have this linear and betas model, okay? The term big data is used, but these methods can apply both to big data sets and small data sets. Okay, so the machine learning distinguishes between two types of learning. Supervised learning is where there's an outcome variable, a y, which is pretty much what we always deal with in economics. Unsupervised learning is when there's only a y, but there's only lots of x's and there's no y. That's done, for example, in psychology. So you've got a number of questions you've asked people, maybe 25 questions, and then, some answers to some questions are similar to others, and you put it through and say, well, actually, given these answers, we kind of identify 4 types of people, right? And we'll call this, combination of X's a type A person and so on. We don't do that very much in economics, okay? So I'm focusing on the supervised learning. And then within that, regression, Y is continuous. That's what we most often deal with. Classification, Y is categorical, right? So a classic example of categorical would be reading a license plate, right? If that first letter in the license plate is a number between 0 and 9, then we're trying to say, given that image, is it one of 10 things? Is it a 0, a 1, a 2, and so on? Okay. Okay. Then to overcome the greediness of chasing data points, the idea is to estimate a model on one part of the data and then see how well it predicts on a different data set, right? And so you get a number of models on your training data, and whichever one predicts best on the other data is the model you want to go with. Okay, so again, that's different from going with statistical inference, or even using, you know, which model has the best adjusted R squared. Okay, so in a machine learning problem, we're trying to fit the data as well as possible, and so you need to say, well, what is a good fit, right? And there are a lot of different measures which vary with different problems, but the standard one for continuous data is mean squared error, right? We just want to look at the average of the squared differences between my actual data and my prediction. Okay, as I said, models overfit. In economics, typically we'll use something like adjusted R squared or one of the information criteria, Arkigis or Bayesian, but which one can use and actually in some cases works pretty well. But what the machine learning literature emphasizes is using out-of-sample prediction using a method called cross-validation, which I'll come to. So there's only a few things, you know, one can take away from a talk like this, but this is one thing you want to take away with, right? Hopefully in a week's time, if someone asks you what is cross-validation, you can explain what cross-validation is. So what we do is we split the data into 5, well, K in general, but 5 equal-sized number of observations. Then for what's called the first fold, I estimate on the other folds, 2, 3, 4, 5, then see how well it predicts on that omitted first fold. Then I do it for the second fold, right? So we'll estimate on the other ones, 1, 3, 4, 5, and see how well it predicts on the 2. Right? We do that 5 times. So we get 5 mean squared errors, measure of fit, and we go with the average of them, and we're going to choose the model with the smallest of these. Okay. So that's the method. And typically, so people have done a lot of studies and suggested that 5 or 10 are good choices, right? Obviously, they're not the best for all sorts of data, but just like, you know, we say we'll test at 5%. These are the kind of normal things to do. And between those, certainly if you had a smaller data set, you'd go with 5. If you had a larger data set, you might see whether to go to 10. And you can go with something in between, 8 if you want. Okay. Okay. So what is mean squared error? The difference between the squared difference between the prediction and the average, okay? There's a result in statistics that says the mean squared error is the sum of variance and the square of bias, okay? Now, in a lot of economics courses, we say you want to use methods to get the bias to 0 and then choose the method that has the smallest variance given that. What the machine learners do is they trade off the two, okay? So what we want is we want as little bias as possible and as small a variance as possible. But you can't do both simultaneously. There's a trade-off, okay? And so shrinkage is a procedure which reduces the variance and at the expense of bias, but it might be when you put the two together that you're better off, okay? So here's an example of an estimator that has no variance, right? I'm just going to say, doesn't matter what the data is, the coefficient is 0, right? Well, there's no variability in that, but it's going to be pretty bad because it's likely to be very biased. Okay, so now I'm going to go through a number of machine learning methods that are going to try and come up with the best y-hat in terms of minimizing mean squared error. Okay, so the first of these are ridge regression and the related method called the lasso. Okay, so ridge was around for a long time, and it has a penalty for the parameters, right? So we've got, maybe I've got here P. So there's P variables in the model. So there's P slope coefficients, and it's going to, we want to minimize, this is the mean squared error of the model, but it's going to give this penalty, and that's going to shrink the betas towards 0. Okay. Then more recently, instead of squaring, people proposed the lasso, and I'll explain the term in a minute, which has this penalty, the absolute value. Okay. The lasso is equivalent, so this thing here, minimizing this, is equivalent to minimizing the mean squared error subject to this constraint with only 2 variables. That's that the absolute value of beta 1 plus the absolute value of beta 2 is less than or equal to something. So this diagram on the right is the lasso. Okay, so we've got 2 regressors. So there's a beta 1 and a beta 2. And these ellipses have a constant mean squared error or some constant sum of squared residuals. And the OLS estimator minimizes that. It's going to be beta hat. Okay, but we've put in this constraint that we have to be in this area. And because of that constraint, because of this square nature, we're likely to wind up at a corner, right? We could wind up anywhere, but disproportionately, we're going to wind up at this corner, this corner, this corner, or this corner, right? And where we're setting one of the 2 to 0, okay? Whereas the ridge, which was around longer, had this circle, and there you're just as likely to be anywhere around here with non-zero coefficients for both. So the lasso was called least absolute shrinkage, that's this bit here, and selection, because it's going to toss out some of the variables. It's going to give them a coefficient of 0. Okay. So in estimating this, so let's go with lasso, we've got the usual betas, and then there's just one extra parameter, lambda, right? And so what's done is you go through a sequence of lambdas, and for each choice of lambda, you estimate the betas, and you decide which resulting beta hats gives us the best prediction in terms of out-of-sample prediction using cross-validation, okay? So you've added an extra thing, which is cycling through the lambdas. But, this is used intensively. There's lots of smart people in computer science and mathematics and so on, and they're very fast algorithms to compute these things. So that's method number 1, okay? Now, all of these methods involve what's called a tuning parameter, right? It's not just the betas. There's going to be some something like this lambda that is, you have to have some rules to come up with it. And Lasso has the advantage that it's relatively straightforward figuring out this lambda. For other methods like neural networks, regression trees, and so on, there's a lot of choices to make, right? Because this is so simple, this is one reason why Stata, its machine learning has Lasso and Ridge, right? Because it's easier to write one-size-fits-all code for them than for other methods, right? And like when you get to neural nets, if you're really good at neural nets and deep learning, right, in the US, you're going to earn several $100,000 a year, okay? If you're good at Lasso, you're going to get a regular salary, okay? Or regular data analyst, you know what I mean? Basic salary, okay. Okay, neural network. I'm doing good. So let's consider two hidden layers, right? Ultimately, Y depends on X, but you have Y depends on W's, right? It's a linear combination of the W's, maybe, and then the W's are a linear combination of the Z's, and then the Z's are a linear combination of the X's. And by doing that, that introduces nonlinearity. It's no longer a simple linear model in X, it's quite nonlinear, right? And the choice here is you have to decide how many hidden layers do I have? And then in each layer, how many W's do I have and how many Z's I have? So clearly, there's a lot of choices to make. Here's a picture, right? So we start with some X's, we put them through some W's, and then some Z's to get the Y. Okay, and okay. So for neural network and for the other models I'm going to talk about, there are some limited Stata add-ons that will do them, but if you really want to use them, now the leading software is in Python, and there's a Python package called scikit-learn that is kind of the leading software, and then R will also have packages for these things. Okay, and what I remember, for when you use Python, the underlying code is in Python, but people have written programs above that, these modules, that really don't require much knowledge of Python, right? The main thing you need to do is be able to read the data into Python. And then after that, you don't need to know programming in Python. You need to know what the scikit-learn commands are, which is a little bit like using Stata, because you don't know what's underneath when you give a regress command. But it is more complex than Stata, but it's not, unreasonably complex. Okay. So another leading method is actually random forests, which are based on regression trees. So a regression tree, it's easiest if I show this with this diagram. So we have two variables, x1 and x2. And what we do is we do a lot of splits on x1 and basically get the mean of y. Well, actually, where the split is, okay, suppose I split here. I'm going to get the mean value of y at either side of the split and then get the sum of squared residual. So it's just like regression on an indicator variable. And I do this all the way along and all the way along here, and I decide which split is the best. And it turns out the best split was on x1. Okay. Then given that, I'm going to consider all splits in this half and in this half. And it turns out the next best split is here, right? So now we've got this, this, and everything else. Then I say, okay, now where's the next best split? And it turns out it was split this area here. Then there's one more split, which is here, okay? And these diagrams are mainly coming from a really good book called Introduction to Statistical Learning by James Whitten, Dibshirani, Hasty. And that book was originally in R, but now it's also in Python. And both books, the PDFs are legitimately freely available on the web. Okay. So this shows the tree, right? I first did a split on X1. Okay, it shows the various splits. And actually here, this is three-dimensional, Y here, X1 here, X2 here, and it's showing how we're splitting up the data, right? Just like, at the end of the day, it's regression on a number of indicator variables for which range X1 and X2 are in, except the data is determining the best indicator variables. Okay. They don't predict very well. So for example, if you split your data into two and then do the tree on one and tree on the other, you'll find you get quite different results, right? So that's one way of showing that it's quite variable. So better methods were picked. One was called bagging. And what that does is that does a bootstrap resample of the original data. So you sample with replacement. Maybe observation 1 comes in twice, observation 2 doesn't come in at all, observation 3 comes in, I don't know, 3 times and so on, and you do it. Then you do another bootstrap sample and another bootstrap sample. The problem with that is, look, if income is really the dominant variable, it's going to come out first every time, right? So instead, random forests average regression trees over many subsamples. So instead of, if we've got 40 regressors, instead of resampling all 40, we say, I'm only going to consider 10 of those regressors. I'll randomly pick 10 and do the regression tree on that. Then I'll randomly pick another 10 and do a regression tree on that. And I'll do it 500 times and I'll average. And it turns out that does very well. And then the splits using these basic methods are in terms of Y, but as you add regressors and you're explaining some of the data, that's going to change which variables matter after that. And bagging, or boosting, sorry, instead uses, boosting, instead of fitting on Ys, it fits on the residuals that you have given how far you've gotten already. Okay, so as I've got here, the random forests get bootstrap resamples, but within each bootstrap sample, you use only a subset, and often M is pretty small, right? If I had 40 regressors, it's saying square root of 40 or 6 or 7 in each resample. Okay. In the economics literature, to begin with, particularly for what I come to later on, causal inference, Viktor Chernozhukov and a lot of co-authors emphasize the lasso, and then Susan Athey and co-authors for their sort of data, they felt that random forests do a better job than the lasso. I think we can skip this. We can just say that these other methods have been around for a long time, and they can also be useful, but they're not used as much. The original way in economics of doing things flexibly was to say, suppose I want to regress Y on a single X, then I'll split the X's, order them, find what the average of Y is for the first 10% of the X's, what the average of Y is for the second 10%, and so on, right? And I get 10 fitted values of Y. Then an adjustment of that is kernel regression, where you roll where you're doing the splitting. But conceptually, it is like splitting into bins. And then if I've got 2 regressors and I split into bins, I've got 10 squared or 100, right? If you get to even 5 regressors, you're going to need a lot of data, right? 10 to the 5. This is called the curse of dimensionality. So these methods would work well if you just had 1 or 2 variables. If you had a lot of x's, economics would put some structure on. So a partially linear model would say part of it is linear, right? And then part of it is, we're not going to impose anything. So for example, if this was electricity demand of individuals over the day, you know, how much they're consuming, this X might be, you know, house characteristics, people's income and so on. And then this would be the time of day, right? A flexible function for how it's varying during the day, okay? Another one is to say, we've got a usual linear regression, but we're going to transform it by some nonlinear function, and we'll let the function determine that. And basically, all these models are reducing it from the dimension being the number of regressors to this is one-dimensional, this is a series of one-dimensionals. If there was a single z, this would be one-dimensional. Okay. So that was the direction that was going, and that was never used very much, right? And Stata only, even now, Stata doesn't have direct commands for these sort of things. Okay. Classification. Okay, how am I doing? So classification is the license plate. Okay. For the license plate, they're finding that the best method is neural net, right? Works very well, but the loss function is different. Instead of minimizing mean squared error, the loss function will just be how many did we get wrong? And we want to, right? So, you know, if we just had 2 possible outcomes, a 0 and 1, the loss function would be, let's add up how many times we predicted a 1 when it was a 0 and how many times it was vice versa, plus how many times it was vice versa. Okay. A lot of the ML applications are to classification, right? And so big advantages are, for example, images, right? Pick out the cat in the photo, right? The machine pick out a flower. And really, it was only about 10 years ago that there was success, okay? And a lot of that was, okay, increased computing power, but neural nets had been around for a long time and they hadn't gone anywhere, right? Partly because of computing needs. It's computationally very intensive. Then when Google wanted to translate from one language to another, they had a translate program, and that used the rules of grammar, right? And right, so it was kind of using domain-specific knowledge. Look, we know what the rules are for Spanish. We know what the rules are for English. Okay. Then a machine learning scientist in Canada at University of Toronto said, look, my group of people are willing to work for one of you people in Silicon Valley, right? Make us tell us what you can offer in terms of salary and access to computing power and so on, and we'll work for you. So for like, I don't know what, $20 million, Google hired this group, and he was a neural net specialist. Within 7 months, his neural net was working better than Google's original Translate program that they've been working on for 10 years, okay? And the big thing about it is it's also scalable. Once you've got the algorithm working well from English to Spanish, there's no reason why, you know, you're not going to have to go away and learn the rules of you know, French. You can apply a similar algorithm to English to French and so on, right? So it's really a big breakthrough, right? And then more recently, you know, again, the classification is the new, you know, chat GBT, the new AI of the last year or two, right? And there, what that's doing is it's not just predicting once. It's, you know, it's not just predicting the first word. It's predicting the second word and given that the third word and given that the fourth word, right? Sometimes that has it going in the wrong direction, but quite a bit of the time it can work pretty well. Okay. Unsupervised learning, we don't deal with that very much. And I'll just say that this is a sort of example. So again, we have no Y now. This is an X1, this is an X2. And this algorithm is saying, you know, if I want to pick two clusters, this looks like it, 3 and 4. And okay, on simulated data. Okay. So how am I doing on time? Good. So the machine learning is focused on predicting, right? It wants to predict a value of Y. It wants to predict, is that letter in the number plate a 0, 1, 2, A, B, C? We don't do a lot of prediction in economics at the individual level, right? It just, because of the data we have, right, it's quite reasonable to believe, right, from my own personal experience and all of ours, that the machine learners do a pretty good job of predicting a license plate, right? What sort of a job will they do in predicting an individual's income, right? If on a log wage regression, you can get an R squared much above 0.3, you've done pretty well, right? So, right, there aren't too many examples where we predict really well at the individual level. However, for a lot of policy things, we're not interested in predicting for each individual. We just want to predict on average. So our models, you know, you give me usual log wage regression, individual characteristics, and years of schooling, right? It will do a pretty poor job of predicting for any individual what their wage is. But it may do a pretty good job of estimating, on average, if someone has one more year of schooling, how much does wage change by, right? And if you find that it's a 10% increase in wage, then, okay, now we say, well, that's a pretty big increase, and it would be worthwhile for the government to provide free education because it's going to increase people's earnings and it can then tax them to pay for the cost, right? So we're interested in predicting on average. This article by Mulleinathan and Spies has a good one, and one example where, not this article, but Mulleinathan has in another paper, is predicting for people over the age of 65 in the US who do have access to health insurance, Medicare, and it's government insurance, and we have very good data using, and there's like I don't know, the data set is, I mean, I don't know what it is. It's of order of hundreds of thousands of people. And it's predicting, given the information we have on these people, we've been following their healthcare over time, let's predict the probability that they will survive another year, right? And then if that probability of surviving another year is fairly low, there's no point in them having a hip transplant operation, right? Because, you know, you have a hip transplant, you're going to be bedridden for a while, and the model's saying you're probably likely to pass away fairly soon anyway. Why not enjoy your, you know, last remaining time without overcoming an invasive surgery? Okay, so there are some applications where we are interested in prediction at the individual level, but mainly it's at the average level. Okay. Okay, so now we know that the people selected how much education they got. So sure, my model tells me 1 more year of schooling, 10% more earnings, but wait a minute, who gets more education? The smarter people, and wouldn't they have learned, you know, earned more anyway? Right. So what we want is you know, if 2 people equal in every respect, and the only difference is one got more education than the other, what was the change in the wage? Right. That's what we want. We want that causal estimate. Okay. And what we want is not just for any individual, because again, I said we're not going to do a good job, but we want to average that over lots of people and get the average causal effect. Okay. Well, the machine learning methods, they're greedy on the data and they don't take account of such causal problems. So what we do is one method that's used is to suppose I've got log earnings, a log wage or log earnings, and then this is years of schooling. And then what I'm going to do is control for everything else. And I'm going to make the assumption after I control for all those other observables, I can believe I've controlled for everything else and I can give this a causal estimate. Okay. Well, that depends a lot on what good use we make of these controls. And what the machine learners we do is we use a machine learner to come up with a much better model for this bit than we would have if I just put in the usual, you know, age squared, years of experience squared, and so on. Okay. So that's what I've got here. A good choice of controls makes the assumption that the error is unrelated to the X, which we need for a causal interpretation. So we can give beta a causal interpretation, right? So we use the machine learner to come up with a good GX2, but we use ML in a way that allows, okay, that's an L, not a K, valid inference, even though we are data mining. Okay, so again, this is fairly recent. The methods started out maybe around 2010. This is a good survey article. Again, Journal of Economic Perspectives is reasonably approachable for good undergraduates. Okay. Why is this not going ahead? Okay. Okay, so I'm going to go to some other stuff next. And I'll try and do this in 7 minutes. Okay, so to be clear, the basic methods, the ridge, lasso, neural nets, random forests, right? They're useful for prediction. For jobs that you might get in private industry, you know, after graduating, that can be enough, right? And having those skills are going to be well valued, right? The causal inference stuff, that's more of interest, particularly to policymakers, right? Really to professional economists, right? And some of you will become professional economists, but quite a number of you won't. So I'm just saying the first stuff is most important, okay? Then I'm going to talk briefly about the causal. The causal uses machine learners along the way. So it uses what we had earlier. In my case, I'm going to be using the lasso, but then it gets difficult to understand, right? To understand what's going on is graduate level economics, right? But that's not going to deter me from briefly going through it. So let's go to these other slides. Here. So we've got this model where, let's just focus on, suppose there's a single variable that we're interested in, like years of schooling, and we've got lots of other things, okay? And what we want is, we don't care about it. At the end of the day, we just want an estimate of alpha and a valid 95% confidence interval and valid t-statistics, okay? Okay. If I have this model, and then I take expectations with respect to all the controls, then I get the expected value of D given the controls, and then the expected value of this thing conditioned on XC. Now it's not stochastic anymore because I'm conditioning on the XC. So that just becomes GXC, okay? So then if I subtract the two, I've gotten rid of this nuisance thing, right? And so these are residuals, the difference between Y and some expected value or prediction of it, okay? So this was proposed in 1988, where these would be fitted using kernel regression methods, okay? The trouble is that in their applications, they're thinking there'd just be 1 or 2 X's, but here we've got lots of X's. So those non-parametric methods don't work. So instead, what was proposed was to use a machine learner. So what we're going to do is use lasso to get good predictions of the Y given all the controls and get a residual. We're going to use the machine learner, the lasso, to get a good prediction here and get the difference. And then we're just going to regress this whole thing here, just an OLS regression, and get the alpha. And we're going to do things in such a way that I can just use the usual OLS output, right? If there's heteroscedastic robust standard errors, I'll get, there's heteroscedasticity but independent data, I just get the usual heteroscedastic robust standard errors. If it's clustering, I get cluster robust, okay? So it's just at the end of the day, a residual on a one or more other residuals. Okay. So I have an application, and okay, I don't. Okay. So if I just did OLS, I'd regress, in this case, log total medical expenditure on an indicator variable for whether people have health insurance, supplementary health insurance or not. And then these contain tons of controls. What I've done is I've interacted I've got levels and squares and cross products of the continuous regressors, discrete regressors, and so on. I don't know. At the end of the day, I have 99 regressors. Okay. So that's what I would do. And then in Stata, all I need to do is, instead of quietly regress, LTOP, I go PO regress, for partially out regress. Okay. The Y, in this case, there's just one X I'm really interested in, and then all the controls, which is lots of them, right? Actually, turns out I've got 176 controls. And I get output that just looks like regular OLS output, right? So it's very easy to implement. However, a couple of things. It does require a choice of lambda for each of the lassos. The lasso for the y variable on all the other x's, and this x variable of interest on all the other x's. And for this, instead of doing a search over lots of lambdas, there's what's called a plug-in formula. It just says, you know, in this setting, go with this lambda. Is that a good lambda? I don't know, but that's what Stata does. There's other software that allows you to try different plug-in estimates of lambda. And then the other thing is, to give this a causal interpretation, we have to believe that all these other controls control for everything else, and what's remaining, the error term is unrelated with the x. In this case, this is a coefficient of 0.18, and it was log medical expenditure. So this is saying roughly, if I have supplementary insurance, medical expenditures are 18% higher, right? More precisely, it's e to the 0.18 minus 1, maybe something like 23% higher. 51, okay, doink, doink, doink. There's lots of things going on, but underlying this is a result that if we've got some estimating equation, we're interested in the alpha, these etas are nuisances, we can do a first order Taylor series expansion, and if this term here has expected value 0, we don't have to worry about the nuisance parameters, and we can use the usual result. And so what you need to use is to choose the right estimating equation in the first place. So for the validity of this method, you've got to be, you know, satisfy this condition, and the PO regress one does satisfy it. And so what's happening now is we go to other models. So this is just for the partial linear model. But for example, well, I just say there are other methods. And for those other methods, actually, people have to get more and more creative. There's other things going on with cross-fitting. I've just shown the simplest method, but I'm out of time. And I did want to show this slide because when you get certainly to the PhD level, right, you see a lot of this, right? Okay, so that is all I wanted to say. I didn't have a conclusion on the previous set of slides, but I'll just conclude by again saying that in most of the world, the machine learning methods are being used for prediction, right? In our economics policy world, where it's a small subset of everything, we actually want to do causal inference. We want to know, controlling for everything else, if I change this one thing, what's the change in the outcome thing I'm interested in? And that gets us into this sort of territory. Okay. Okay. Thank you.
We can take 1 or 2 questions. Someone?
Don't be shy.
No questions? No, nobody wants to ask anything. Paloma?
Hi, yeah. Well, I don't know if it's a good question, but why we need to learn machine learning, and how it's correlate with IA, like the AI. Sorry.
Question is, how is machine learning related to artificial intelligence?
Yeah, exactly.
Okay, so artificial intelligence has many meanings, right? So from a psychology point of view, it's being able to think like a human, right? But that's not what they're saying when they say artificial intelligence. It's basically prediction using machine learning is what artificial intelligence is, right? So that's what ChatGPT is using.
Yeah, exactly.
But it's a more complex prediction thing than here because, as I said, it's not just trying to predict what the next word is. It's trying, given your question and given what it's already written, what is the next thing, right? And that's called generative AI, and it's just very recent. And you know what I read, all the experts just even can't believe how quickly things have happened in the last couple of years. And the generative AI is enormously computationally intensive, right? So, and people think this is a goldmine, right? We can, have, instead of talking to someone, you can have a computer answer the question for you. And so everyone's scrambling to be able to do this, to be the first entrant and so on. So first of all, you need computers, and the computers rely on, nowadays what they use is a GPU, graphical processor unit. And so the demand for those have gone sky high, and NVIDIA might become the most valuable company in the world. But secondly, when you put them into a data center, there's an enormous use of electricity, right? And already in the US, they're realizing, people are buying up land, put a data center in a city, and the city electric utility is saying, wait a minute, we don't have the electricity to supply you to run it, right? And there's going to be an enormous increase in energy consumption as a result. Yeah.
Thank you.
Hi, thank you for the talk. I just wanted to ask if you know where could deep learning be applied in economics?
Well, deep learning is really neural nets. Okay, so first of all, if you're interested in straight prediction, there are for some types of data, a random forest might work better in prediction. For other types, a neural net might work better. But I think over time, people are leaning more and more towards a neural net, or deep learning is pretty much the best thing for everything. But there was more to your question. What was the rest of the question? Okay. Yeah.
That was it. Thank you.
Yeah. Oh, okay. Yes. So the other part of it is for prediction. The original work by Chernozhukov was done using the lasso, but the methods apply to any machine learner, right? So the example that I went through at the end with PO regress, that's relying on a lasso to come up with, the best prediction for Y and B given the controls. It may be that you could do better in prediction and controlling for the other things if you used a neural net or if you used a random forest, right? And we're at early days in, learning what's best. And again, even there, it may be for some sorts of data, when you do this partial linear model, one sort of machine learner is better, and then for another one, a different one is better. Yeah.
My question is, how relevant will machine learning be 5 years in the labor market?
So that's hard to know. I mean, so many people are getting into data analysis now, and eventually it's going to be maybe a little bit like computer programming, right? And if you're 40 years old and you haven't kept up with the latest changes and so on, you might find it a tough labour market. Eventually, that's going to be true for AI as well. But, who knows whether that's in 5 years or 10 years or what. The other thing is that, I don't know, whatever you choose, you want to enjoy it, right? Don't get into AI unless, first of all, there's going to be quite a bit of coding, so you want to be interested in coding and have some strength there. I'm lucky because, in my case, I'm applying it, or at least teaching methods for economics applications, and I'm really interested in economics applications, right? So yes, you want to, and then I just believe if you're strong in machine learning, then you're strong in STEM skills, and that's got to be rewarded in the job market, right? Even if eventually it's not in AI, it's in something else.
Thanks.
Hi, I have a specific question.
No, it's fine. Okay. Yeah. Sorry. Yes.
Yeah, it's about the dimensionality of the model.
Yes.
The model is gonna do by itself. Like if you have a lot of constraints on it, it's gonna get rid of all of them by itself. Or should you first use some reduction dimensionality model like a PCA,
yes.
and then use another machine learning model? I don't know.
Yes. So in general, most methods start with a really big model. So the Cherny-Zhukov et al. Stuff, what they do is, given the x's, they take all the interactions as well and the squares, right? And then that's felt that that's fairly flexible, but you could do even more. Now, for some methods, if you have more, controls, the number of observations, you're in trouble. But actually, the lasso is okay. The lasso will handle more because it's going to start throwing things away. If computation was an issue, right, then you might consider doing things like principal components along the way to try and reduce the model. And then a joke that I tell, so I shouldn't say it's a joke because then now you feel you have to laugh, is that in prediction, if you're not in the policy world, but the commercial world, you don't necessarily have to predict very well, right? The first thing is you just need to be able to predict better than other people, all right? But secondly, actually, all you need to do is persuade people that you can predict better than other people and you can make money, right?
Thank you.
Well, I want to know which is the best way to start learning machine learning. How can we start? Because I think that what you have taught us today, it's really interesting, but I don't know where to start.
Okay. So let me go. Okay, so as far as the text goes, not good. These books, An Introduction to Statistical Learning with Applications in R, and then more recently, there's an edition, there's a second, second edition, there's one in Python, right? And that explains the code as well, right? So you can go through things on your own, and R and Python are freely available. If a course is offered, take the course. If it's clear what you're going to use, R, Python, or whatever, take a course. I think if you're really serious about this, I said you don't necessarily need Python, but I think Python is something to consider taking, right? In the university, I don't know whether you have access to these courses, but the university would offer courses in Python. There are probably some courses out on the web now that are free courses in getting going in machine learning through companies like Coursera. And if you want to get a certificate for having done it, you'll need to pay.
Yeah.
But I think quite a bit of it is just learning by doing, right?
Okay.
More than a lot of other things. Yeah.
Well, thank you.
What do you recommend to what do you recommend are the advantage or disadvantage for using Stata or Python for machine learning? What are the recommends?
Okay. So for Stata is a good place to start, right? And my book, the chapter 28, right? This provides an overview and examples using the lasso, right? I think that's a good way to begin, but Stata is limited, right? If you want to go beyond machine learning, lasso and ridge, then the decision is really, do I want to be in the R world or the Python world? Okay. And if you're doing a lot of statistical analysis and regression and doing some machine learning on the side, maybe R, because R is set up for that. If you're just more exclusively machine learning, then Python and scikit-learn. And Python also does have a module now, stats models, which does quite a bit of the stats that R does, right? But in my case, it's a pain, right? I used a lot of languages before I got into Stata. I wrote a book in LimDef, and people said, well, this is great, and I had all these examples. Do you have them in Stata, right? That's when I switched to Stata. I do stuff in R and I do stuff in Python when I'm teaching, and I have to relearn it every time. I mean, it's just very inefficient, and there's benefit. You know, it's a hard choice, but I would say, am I going to be an R person or a Python person? And then be aware, even if you make that decision, maybe in 5 years' time, you have to switch over. Yeah. But definitely, actually, on Stata, a lot of people shy away from Stata. It's not real like R, right? If you can do it in Stata, do it in Stata. It's simpler, right? If you can't do it in Stata, then yes, definitely you want to go and use something else. Right. Plus, Stata costs money.
So this is a speculative question, but with these new tools that we have at hand, are there new ways to approach old questions in economics, maybe with new data sets that we were previously not able to? So the reason is that maybe I think the sorts of data that we used, you know, like GDP coming from national accounts or data coming from the representative surveys, maybe responded to a framework where we were trying to extract sort of population parameters, like how much does an extra year of education improve incomes? And maybe these sorts of methods are very different, right? In the sense that they're not focused on population parameters, but maybe predicting and so forth. So basically the question is, are there new sorts of data that we could use to answer economics questions, and even maybe sort of gathering new data to answer them?
Okay, so on the macroeconomic side of things, there's been more done now to work with many series, right, that are related to each other. But those methods at the moment don't really use machine learning, and that's stuff I'm less familiar with. For microeconomic policy analysis, the big breakthrough has been developing new, basically causal methods using observational rather than experimental data, right? So the quasi-experimental revolution, right? So once upon a time, the main causal method would have been instrumental variables, and you had to justify why your instrument was a valid instrument. Then we got to things like, well, I went through the partial linear model example. So the partial linear model example, first of all, you've got to believe that, you know, it's linear in the variable of interest and so on. But given that that model's okay, the crucial thing is to have a good set of controls. And what the machine learner has enabled us to do is to make better use of the controls so that our assumption that the error is uncorrelated with the variable of interest is more reasonable. So the machine learner we've had to make assumptions to do our analysis. The machine learning methods, because they're better at predicting some subpart of the problem, can make our assumptions more plausible, I'd say, is the biggest thing. Then the other revolution has been that even though I wrote out a model that looks like it's the same alpha for everyone, actually we can allow different people to respond differently and get their average effect, right? So that's another part of the class. So heterogeneous effects. Okay, so then maybe this is one example. If you do a drug trial, right, all they do at the end of the day is a difference in means test. Okay, so, you know, and on average, if the response is better with the treatment than without, and it's statistically significant at 5%, we're okay. But wait a minute, the treatment was still only working on 40% of the people. Wouldn't it be good if we could identify which people that it's working for? Well, that's a machine learning problem. But again, I mean, that's a prediction problem, but we're going to be data mining. So people, Susan Athey and Stefan Vargas, and Hito Imbens, are developing methods that would allow us to data mine and using what they call honest forests and identify which type of people does the treatment seem to be working the best for, right? So that might be one of the sort of examples that you're looking at where we can go further. Yeah.
Can I ask you a question? Yeah. So you said as an example how to use this new machine learning for identifying variables that are not correlated with the errors. So that is a typical problem of endogeneity in econometrics. Machine learning helps us to find that set of variables. So that is a problem that helps us to face the omitted variables problem.
Yes.
Now, there is another problem that is called simultaneity.
Yes.
And do you think we can use these methods to face that?
Okay, so the old way of dealing with endogeneity was to write out a full model, right? Y1 depends on Y2, Y2 is endogenous, then Y2 may depend on Y1. So you have a system of equations, and then if we put some exclusion restrictions in the model, it's identified. Okay. The quasi-experimental revolution has thrown that away and it's just said, look, I'm just going to model Y1. It depends on Y2, but I'm not going to have a model for Y2, right? I'm just going to assume, let us assume that there is an instrument, right, without writing the full model. So we've moved away from that. But basically, we're not having to put as much structure on the problem. I mean, I hadn't thought about your question. I don't think we're going to go back to. Yeah. I don't see how machine learning would help there, but that doesn't mean that it wouldn't. I can't think of a way that it would help. Yeah.
So, any other question? No, I think not. So we must thank to Dr. Colin Cameron, and thanks to you for coming. Before you go, I wanted to hacer una porra de la UNAM para despedir al doctor, ¿no? Okay, un aplauso y una porra.
Yeah.
Okay, so.
Thank you.
So, México, Pumas, Universidad, Goya, Goya, cachún, cachún, ra, ra, cachún, cachún, ra, ra, Goya, Universidad.